Okay, next we have Poisson's equations and Laplace equations. We will have these two kinds of equation. We will call it a Poisson equation, and the other one is called Laplace equation. So I will start from the fact that we know that electric field can be written as the negative gradient of potential. We already did too many times that electric field is equal to the negative gradient of potential. This is equation 1. And we also know that the differential form of Gauss's law, the differential form of Gauss law is del dot E is equal to rho over epsilon naught, where rho is the volume charge density and epsilon naught is the permittivity of free space. So this is the Gauss's law for free space. This is, let's say, equation number 2. Now if we put equation 1 and equation 2, like using equation 1 and 2, we have what we get? We get del dot E. So instead of E, I will put minus del V, which is equal to rho over epsilon naught. I can write it as like this: del dot del V is equal to minus rho over epsilon naught. Now this del dot del V, we can write it as del square V, which is equal to minus rho over epsilon naught. This is equation number 3. Now equation 3 is called Poisson's equation. Poisson's equation. This is called Poisson's equation. Now in this equation, del square is called Laplacian operator. And this del square can be expressed as partial square or partial x square plus partial square or partial y square plus partial square or partial z square in Cartesian coordinate. In Cartesian coordinate. So the Poisson equation in Cartesian coordinate will become partial square. So here we have partial square over partial x square plus partial square over partial y square plus partial square over partial z square, and here we have this v, which is equal to minus rho over epsilon naught. We can write it as partial square v over partial x square plus partial square v over partial y square plus partial square v over partial z square, which is equal to minus rho over epsilon naught. This is Poisson's equation in Cartesian coordinate system. Now, if charges are distributed such that there will be some point where the charge density becomes zero, it's possible. So for such case, like in region where there is no charge, if there is no charge, then the charge density, that is the charge density, will be zero there. So for this case, equation 2, for such situation, takes the form del square v is equal to equation 3, equation 3 for such situation takes the form. Equation 3 is this one, which is on the right hand side, on the left hand side we have del square v, which is equal to, on the right hand side we have rho over epsilon naught, while the charge density is 0, so we have the right hand side equal to 0. This is called, I call it equation, this is equation 4, then I call it equation number 5. Equation 5 is called Laplace equation. Now we know that this is Laplace equation. Now I will do some extra calculations here. We know that the curl of electric field is always 0. We did it before and we already proved it there. Now I will prove this fact again here. Like we will prove this by using equation 1. We will prove that this del square E, the curl of E is equal to 0. We will prove this fact by using equation 1. Equation 1 is, where is our equation 1? Equation 1 is this one. E is equal to minus del V. Equation 1 is E is equal to minus del V. Like the electric field is the negative gradient of the potential. This is equation 1. We will prove this by using equation 1 and this quantity del cross E. Now del cross E, or the curl of E, will be equal to curl of E. E is now minus del V. We can write it as minus, I will keep it outside, so we have del cross del V. This is curl of gradient of potential, and we know that we already discussed this in the introductory part of electrodynamics course, that the curl of gradient of any scalar is always 0, and the scalar here is the potential. So we can write it as the curl of E, which is equal to minus curl of gradient of scalar potential, and this is already 0 because we already proved it. So if it is 0, this implies that this curl of E is equal to 0. So we prove this again by using the fact that electric field is the negative gradient of potential. So I will stop my video here, and I will proceed in the next video. Thank you.